The more we learn about exoplanets, the more we realize the universe is stranger than we ever knew. Although the universe is full of miracles, it also has celestial nightmares, planets that defy imagination and cast doubt on our understanding of the cosmos. It's almost unreal to think that scientists hadn't found a planet outside of our solar system until the early 1990s. Scientists were positive that other stars orbited other stars, but there wasn't much proof of other planetary systems. As of right now, researchers have discovered more than 5,000 exoplanets and believe that most stars are part of different solar systems. While some exoplanets have proven to be more exotic than anything we could have imagined, others have surprised us by showing striking similarities to fictional worlds from our imaginations. Our universe is estimated to have over 100 billion galaxies, each with hundreds of billions of stars. There could be billions of trillions of planets in the universe if the majority of stars have one or more planets orbiting them. Each new finding of an exoplanet contributes to our understanding of how the universe works. When we just had our own solar system's 8 planets to study, we had a limited view of what kind of planetary systems are possible in the cosmos. But now, with more than 5,000 exoplanets in the database, planetary research is reaching new heights. In addition, sometimes we see the formation of other star systems, providing insight into our own origins. It's like watching our very own How It's Made show through the world's telescopes. As we discover more about planets outside our solar system, a surprising fact has begun to emerge. The universe is weird, really weird. But maybe nothing is scarier than the thought of finding yourself on a scorching planet with erupting volcanoes, iron rain, or extremely high temperatures. These horrifying planets are perhaps the last place you want to be, especially if you're alone. Let's journey through the darkest corners of space and explore these chilling worlds. Life is really nothing but the relentless onward march toward death. And most people don't like to be reminded of that sort of thing. However, that's what makes us as humans, right? It turns out that we're not really that unique after all, and astronomers have been studying the planet WASP 76b's slow death spiral for a while now. The planet was initially discovered in 2016, with the use of the wide-angle search for planets observatories, which are equipped with several wide-angle cameras to search for telltale brightness dips caused by an orbiting planet periodically passing in front of the star. About 640 light-years away from Earth, WASP 76 is a star that is 500 degrees Celsius hotter and 50% more massive than the Sun. WASP 76b is a planet with 1.8 times the width of Jupiter and only roughly 90% of its mass. This suggests that it has puffed up and expanded as a result of the star's heat. But why? The orbit of WASP 76b is very short, spanning only 1.8 Earth days, and it revolves around the star at a distance of only 4 million kilometers above the surface. Surprising, right? Even Mercury stays about 10 times farther from the Sun than that. Hence, WASP 76b is referred to as an ultra-hot Jupiter. Now, let's understand why orbital period is so important for us. The amount of time an astronomical object needs to complete one orbit around another object is known as its orbital period. It is significant because it can help in our understanding of how celestial bodies, such as planets, spacecraft, and galaxies, moves in space. For example, there are roughly 365 days in a year on Earth. Why does that count as a year? The time it takes for Earth to complete one full orbit around the Sun is approximately 365 days. In our solar system, every other planet likewise revolves around the Sun. How long does a year last on those planets then? Well, it depends on where they are orbiting. The night sky changes throughout the year due to Earth's orbit around the Sun, making some stars visible only in specific months. Satellites can also benefit from orbital period. For instance, a geosynchronous Earth satellite can stay above the same location on Earth because of its one-day orbital period. The satellite is always in the same position, which makes it helpful for weather observation and communication. Planets that orbit closer to the Sun than Earth have shorter years than Earth. However, planets that orbit farther from the Sun than Earth have longer years than Earth. This happens because a planet's orbital path around the Sun is relatively short if it is close to the Sun. We refer to this distance as an orbital path, and hence, the closer a planet travels to the Sun, the more the Sun's gravity can pull on the planet. The stronger the pull of the Sun's gravity, the faster the planet orbits. But why are years on other planets important to us? Understanding how other planets orbit the Sun is important to scientists because it facilitates space travel to those planets. For example, we must ensure that we know the location of the planet in its orbit if we want a spacecraft to reach it safely. Additionally, we need to make sure that we avoid colliding with any other planets or asteroids that are in orbit. Scientists who study Mars also need to keep a Martian calendar to schedule what rovers and landers will be doing and when. Since WASP 76b orbits close to the star, it is most likely tidally locked, meaning that its day and year are both 1.8 Earth days long. This means that WASP 76b spins once for each orbit. However, being a gas giant, it doesn't have a surface, but it's likely the gas on the side facing the star heats up so much it expands and flows around to the planet's night side. The temperature at the cloud tops is estimated by physics models to be about 2,400 degrees Celsius or 4,400 degrees Fahrenheit. It is so hot that scientists say it probably rains molten iron. The rocks would melt on the day side. They then evaporate and condense back on the night side. This could create clouds composed of iron particles that would then drip molten iron rain. The researchers examined WASP 76b using the Echelle spectrograph for rocky exoplanets and stable spectroscopic observations, a device mounted on the Very Large Telescope of the European Southern Observatory in Chile. Nonetheless, the iron signal of WASP 76b was not evenly distributed. It was detectable not just during the planet's nighttime transition, but also during its evening phase. The team could discern this from the amount of light they saw on either side of WASP 76b, which correspond to the boundaries between day and night. Astronomers believe that the iron condenses into clouds as it reaches the colder, darker side of the planet, since the evening shift causes a sharp drop in temperature. This might suggest that liquid iron droplets fall from the sky during WASP 76b's nighttime hours. and that rain probably isn't sprinkling down in a gentle mist, because the big temperature disparity between WASP-76b's two halves generates winds of startling ferocity. For example, the iron in the planet's dayside air is traveling at a speed of roughly 11,000 miles per hour, or 18,000 kilometers per hour toward the night side. But hold on, it gets better. Have you ever seen a glory? Glories are bright, circular rings of light that are only visible in specific situations. They are frequently visible from airplane windows. They're fairly common to see on Earth, and astronomers have also seen glories on Venus. However, on April 5, 2024, researchers announced that they had discovered the first ever glory on WASP-76b outside of our solar system. They claim to have found the glory by utilizing information from the NASA Transiting Exoplanet Survey satellite and the ESA's characterizing exoplanet satellite space observatories. If this is indeed a glory, which is still yet to be fully confirmed, it will be the first one ever to be observed outside our solar system. The reason why no glory has ever been witnessed beyond our solar system is because it needs very peculiar circumstances. In order to study air particles for an extended period of time, they must first be nearly perfectly spherical, uniform, and stable. The observer, in this case Cheops, must be perfectly oriented, with the planet's nearby star needs to shine directly at it. It seems that the glory is located halfway between the planet's day and night sides. Similar to glories seen here, it likely occurs when sunlight is reflected off clouds made of a uniform substance. That material on WASP-76b, however, is still a mystery. So, how did the astronomers detect the glory? The planet's transit, or passing in front of its star, as observed from Earth, provided the first clues. The planet's limbs, or outermost borders, were strange. Over a 3-year period, the researchers observed WASP-76b 23 times. Something strange caught their attention during that period. The eastern terminator of the planet, which separates day and night, was a source of light that they observed in greater quantities than they had anticipated. What could be the cause of the brightness change? The brightness of an exoplanet, or its phase curve, has never been found to fluctuate so drastically. This finding leads us to postulate that the unexpected glow may be the result of the glory effect, which is a strong, localized, anisotropic, directionally dependent reflection. However, what makes discovering a glory on an exoplanet important? First, it's already a relatively rare phenomenon in our own solar system overall. Thus, the discovery of glories on exoplanets indicates that such events can occur elsewhere. It also offers hints regarding the atmosphere of WASP-76. It implies that clouds composed of precisely spherical droplets must exist. Based on current observations, it appears that they have a longer lifespan than 3 years, or that new clouds are formed on a regular basis. That in turn requires temperatures to be stable over long periods of time. Furthermore, the ability to identify glories will aid astronomers in observing other weak occurrences, such as sunlight glinting on exoplanet lakes or seas. There is also just the intrigue and satisfaction of finding something new and unique. Iron may be vaporized in WASP-76b's atmosphere to the point that it condenses on the colder night side and rains forth. Indeed, WASP-76b might experience molten iron showers. This theory is controversial, since the planet's atmosphere is chaotic due to the extreme temperature variations between day and night, strong winds, and rapid rotation. It's also plausible that other factors could be responsible for the iron found in the planet's air. But the point here is that telescopes and cameras are getting good enough to remotely and metaphorically sniff the air on planets hundreds of light years away, and astronomers can use that data to investigate conditions there. One last thing to consider is that some planets differ greatly from those in our own solar system. Furthermore, WASP-76b is by no means the hottest exoplanet that has been discovered. The universe is strange and often extraordinarily inhospitable to human life. We can't help but wonder. In the last 25 years, we have uncovered more than 5,000 exoplanets, exploring a little portion of the galaxy. There are 200 billion stars out there, and a decent fraction of these have planets orbiting them. What other amazing and bizarre planets will we find? Have you ever considered the possibility of a planet made of diamonds? Although it may sound like a sci-fi idea, scientists have actually found a planet that appears to be almost completely composed of diamonds. The planet, formerly named 55 Cancri E, was found in 2004 and is situated in the Cancer constellation, around 40 light-years from Earth. Being a super-Earth exoplanet, 55 Cancri E shares compositional similarities with the rocky planets in our solar system. But its mass is 7.8 times more than Earth's, and it's almost twice as big. In comparison to Earth's 365-day orbit, its orbit is extremely short, taking only 18 hours to complete, and it orbits very close to its star. Compared to Mercury's distance from the Sun, the alien planet is 26 times closer to its parent star. The Earth beneath our feet would warm up to roughly 3,200 degrees Fahrenheit if Earth were in the same location. The planet is most likely tidally locked, which means that, like the Moon toward Earth, it always faces the same direction toward its star. This would indicate that one side of the planet is always exposed to radiation and heat from the host star, while the other is continuously plunged into darkness. Furthermore, 4 other planets, all gas giants, are known to orbit its host star. The system consists of a K-type star, designated 55 Cancri E, also named Copernicus, is a star similar to our Sun. It is smaller in radius and slightly less massive than the Sun, and so is cooler and less luminous. It has an apparent magnitude of 5.95, making it just visible to the naked eye under very dark skies. However, what makes 55 Cancri E truly unique is its composition. Scientists believe that the planet is made up of mostly carbon, which has been compressed to form diamond. According to estimates, the planet may contain up to 3 times as much diamond than has ever been mined on Earth. So how did 55 Cancri E become a diamond planet? The planet is thought to have developed initially from a mixture of metal and rock, much like Earth. However, because of its close proximity to its star, it experienced extreme heat and pressure, causing the carbon to crystallize and form diamond. As 55 Cancri E orbited its star, the James Webb Space Telescope was used to study variations in brightness. Infrared light coming from the exoplanet was captured by Webb's mid-infrared instrument and near-infrared camera. As the James Webb Telescope opens new doors to exoplanet exploration, the discovery of a rocky one with an atmosphere has been a groundbreaking find. In the past, all of the previous exoplanets found to have atmospheres were gaseous planets, not rocky ones. The discovery on 55 Cancri E has marked the first time a rocky planet beyond our solar system has been proven to have an atmosphere. The atmosphere of Earth provides protection from solar radiation, warmth, oxygen for human living, and the pressure required for liquid water to remain on the planet's surface. The atmosphere is essential to life on Earth. This finding on Planet 55 Cancri E raises the possibility that Webb might carry out comparable studies on planets that are much cooler than 55 Cancri E and may have liquid water on their surfaces. But we are not there yet. Though it may be tempting to consider 55 Cancri E as a massive diamond in the sky, the planet is likely to be much less glamorous than we might imagine. It seems improbable that humans will ever be able to explore the planet in person because of the tremendous pressures and temperatures that would make it an extremely hostile habitat for any form of life. Despite this, the discovery of 55 Cancri E has given scientists new insights into the formation and composition of planets. It serves as an intriguing reminder of how diverse and unexpected our universe can be. Looks a bit like Earth, doesn't it? To the human eye, this far-off planet looks bright blue. Any space traveler, however, would be gravely mistaken to confuse it with Earth's friendly skies. However, you wouldn't find this planet very comfortable. Known as HD 189773b, it rains glass sideways and has a surface temperature of more than 1,000 degrees Celsius. This planet is located in the Vulpecula constellation, roughly 63 light-years from Earth. Because HD 189773b is blue, it resembles Earth. Its actual hue has been discovered by astronomers, a first for an exoplanet, a planet circling a star other than our Sun. Similar to Earth, this alien planet is a beautiful blue dot in a sea of pitch-black darkness. But that's where the similarities between the two worlds end. To begin with, HD 189733b is a planet roughly the size of Jupiter that orbits its home star every 2.2 Earth days. It is also significantly hotter than Earth. The exoplanet is most likely tidally locked, continually exposing one face to its star because of how close its orbit is to it. If that's not crazy enough for you, scientists think the rain on this world is made not of water, but of molten glass. The temperature of the planet's surface may lead the particles to condense and turn into glass. The wind on the planet would then carry these glass particles around at 4,000 miles per hour or 7,000 kilometers per hour. And getting caught in the rain on this planet is more than an inconvenience. It's death by 1,000 cuts. Scientists believe silicate particles give exoplanets their blue color, whereas Earth's blue tint comes from light reflected off its seas. In 2007, spectroscopic data from the Spitzer spacecraft showed that water vapor was present in HD 189733b's atmosphere. This finding confirmed the theory that hot Jupiters, like this exoplanet, are wet, as some theorists had predicted. High winds, a hot, sun-facing side that is warmer than its dark side, and past studies of HD 189733b from Spitzer and other ground and space-based telescopes imply that the planet may have dry clouds, even if its water is too hot to condense into clouds. Additionally, the discovery implies that water, an essential component of life as we know it, is commonly present on planets throughout the universe. Methane was also discovered in the atmosphere of HD 189733b in 2008 by Hubble telescope, marking the first time in history that an organic molecule was discovered in an extrasolar planet's atmosphere. With its highest photometric transit depth to date, This exoplanet causes a 3% drop in light received from its host star when it passes in front of it. Additionally, new analysis of the planet show that this exoplanet has a much larger outer atmosphere than predicted. All of these unexpected discoveries indicate that, despite being hostile to life, the so-called hot Jupiter alien planets are interesting enough to investigate separately. Hot Jupiters are large, roughly Jupiter-sized planets that become very hot by circling tight around their stars. Because these worlds orbit so near to their parent stars, they face the risk of being devoured. They have been dubbed planetary daredevils. When a hot Jupiter passes in front of a star, its disk blocks out a significant amount of the star's light, making it easier to identify the planet from a distance. For example, HD 189733b causes a 3% drop in the star's light. The parent stars of these planets often wobble due to the planet's gravitational pull. Hot Jupiters, however widespread in the universe, are completely different from what people on Earth experience within our solar system. In our case, small, rocky planets orbit close to the star, and the gas giants are much farther out. One of the reasons scientists are paying more attention to hot Jupiters these days is that the most recent measurements of HD 189733b are casting doubt on several planetary formation theories. A few investigations have shown that this exoplanet is home to potential exomoons. In 2014, scientists postulated the existence of a moon by examining the periodic variations in the amount of light emitted by the exoplanet. It is implausible that this moon exists because it would be outside of the planet's Hill sphere. But it's not simply unusual and hazardous weather that makes this exoplanet interesting to astronomers. The exoplanet's atmosphere is rapidly being torn away to space because it is absorbing such a high amount of strong radiation from the stars in the HD 189733 binary system. All may not be lost, however, as another extreme exoplanet demonstrates that sometimes depleted atmospheres get a second chance. Earth is the only planet we know of that harbors life, but it may not be alone in the universe. Meet Kepler 452b, the first nearly Earth-sized planet discovered in the habitable zone of a star, similar to our Sun. This orbital region is where a planet like Earth may have liquid water on its surface and potentially sustain life. Kepler 452b was found in 2015 within the data that the Kepler satellite had collected prior to the first phase of the mission ending in 2013 due to a reaction wheel failure that prevented Kepler from staying pointed at the same location in the sky for 4 years. The star Kepler 452, which is found in the Cygnus constellation, is the object around which this super-Earth revolves. Similar in brightness to our Sun, this star is too dim for us to view from Earth without a telescope. Kepler 452 is about 1,800 light-years from Earth. The Kepler Space Telescope made the discovery of Kepler 452b. Kepler's method of planet discovery is a sophisticated and remarkable one. We all know that planets don't emit their own light. They do reflect the light from their stars, but that reflected light's intensity doesn't take a stand in front of its highly luminous star. Thus, we are unable to directly see any planets. The Kepler telescope monitors a star's brightness. When the orbiting planet passes between the star and the telescope, we detect a subtle decrease in that star's brightness. The brilliance of the star is reduced more when the planet is large and less when the planet is tiny. However, if the brightness reduction is noticed over an extended period of time, the planet likely has a larger orbitum and takes longer to orbit its star. Thus, we may determine a planet's diameter, its distance from its star, its orbital period, and ultimately the mass of the star by accurately measuring the brightness of the star. Kepler 452b is sometimes referred to as Earth 2.0 or Earth's cousin, and some astronomers have given it the name Coruscant, which is the name of the home of the Galactic Empire in the Star Wars films. We do know that it has some things are in common with the Earth. To give one example, Kepler 452b orbits its star in 385 Earth days, which is little more than an Earth year. Another good thing is that the planet lies in the Goldilocks zone, which is the perfect distance between a planet and its star, where it is neither too hot nor too cold for life to survive. The same is true of the Earth in our own solar system. Mars is too far away from the Sun and is too cold for water to freeze. Venus is too close to the Sun and is so hot that water would boil. However, water can exist on Earth and Kepler 452b at precisely the correct distances from their stars, with temperatures ranging from 0 to 100 degrees Celsius. Astronomers have also managed to measure the size of the planet Kepler 452b. They are able to accomplish this because, as viewed from Earth, the planet crosses in front of its star once every orbit. This causes a little portion of the star's light to be blocked by the planet, making it appear somewhat fainter for a few hours. Kepler 452b's size has been estimated by scientists to be roughly 1.5 times that of Earth, based on measurements of the amount of light dip. If the star Kepler 452 was closer to us and therefore brighter, astronomers could measure how much it wobbles, as it's pulled backwards and forwards by the planet orbiting it. They could then calculate Kepler 452b's mass using that measurement. Although this isn't possible, we can still make a good guess about the planet's mass. Kepler 452b's mass must be roughly 5 times larger than Earth's if it is composed of rock, as the Earth is. This implies that gravity on the planet is roughly twice as powerful as it is on Earth, meaning that you would weigh twice as much and it would be twice as hard to jump. Since Kepler 452b is too far away to obtain a good look at, further speculation is needed to imagine other aspects of life on the planet. However, if the planet is indeed super-Earth in size, it might have a large number of active volcanoes. It might possibly have a cloud-covered atmosphere that covers the majority of its surface. We're not sure if you could breathe the air there, because we don't know what the planet's atmosphere is composed of. However, the oxygen and nitrogen content is probably not going to be the same as in the Earth's atmosphere. Additionally, models indicate that Kepler 452b may soon encounter a runaway greenhouse effect, similar to the one that transformed Venus from a potentially habitable planet billions of years ago into the stifling hothouse it is now. Kepler 452b's star is apparently older than the Sun 6 billion years, compared to 4.5 billion years. Because of this, the star is in a more energetic stage of its life cycle than the Sun. In fact, the star is 20% brighter and 10% larger than the Sun. This implies that although earthly explorers would be used to Kepler 452b's sunshine, it would not be quite the same. The increased energy output of its sun might currently be causing this super-Earth to heat up and lose its oceans. If the planet does indeed harbor oceans to evaporation, subsequent breakup by ultraviolet light and atmospheric escape. If predictions of the planet's size and the star's age are correct, such a scenario probably won't happen on Kepler 452b for another 500 million years or so. While this exoplanet may not be an exact replica of Earth, it is most likely the closest Earth-like planet discovered to date. So let's assume if we want to travel to this super-Earth today, how far away is 1,400 light-years? Well, that will be a very, very long journey, even in science fiction. If current technology is used, getting to Kepler 52b could take so long that before the spaceship reaches its destination, humans could go extinct. NASA's New Horizons probe, which recently sent back amazing photos of Pluto, would take around 20,000 years to travel 1 light-year. At that pace, it would take 28 million years to reach Kepler 452b. It's not hard to imagine human beings would look completely different by the time a spacecraft launched today reached its remote destination. While advanced engines would make the journey shorter, reaching Kepler 452b still looks like an impossible dream. The Dawn orbiter's electrically powered ion engine is far more effective than the chemical thrusters used by earlier missions. With the NASA Evolutionary Xenon thruster, the agency hopes to enhance that ion engine concept and enable future spacecraft to travel at speeds of up to 90,000 miles per hour. At present time, Dawn can travel 9,600 miles per hour. That may sound fast. However, based on estimates, the journey to Kepler 452b would still need 10.5 million years. What if we created something even more advanced? Physicist Freeman Dyson developed the concept for Project Orion in 1958. It would use pulsed nuclear explosions to move a giant ship forward at around 5% the speed of light. A spacecraft traveling at such speed would take 28,000 years to arrive at Kepler 452b from Earth. Yes, that would be an upgrade, but it would be hard to convince people to go on a journey that would last longer than the history of human civilization. We would need something like an antimatter engine to make the travel even remotely possible. Though it sounds like science fiction, antimatter is real. It's matter with the electrical charge reversed. For example, an antiproton is a proton that has a negative charge instead of a positive one. When antimatter meets matter, it creates a massive amount of energy, something that theoretically could power a rocket engine. But we have one major problem. NASA estimates that producing 1 milligram of antimatter in a particle accelerator would cost $100 billion. For scientists to utilize the material to power a spacecraft engine, it would first need to be produced in large quantities, and then the intense energy from a matter-antimatter reaction would need to be collected. Some experts think an antimatter engine might accelerate a spacecraft to 70% the speed of light if humans could figure it out. Reaching Kepler 452b in such scenario would require 2,000 years. That is still a long time. 2,000 years ago, the Roman Empire was around. If humanity were to arrive at Earth 2.0, they would most likely need to rely on a multi-generational ship that could support over 100 people and maintain genetic diversity while still having enough power to care for them and future generations. The people on the ship would have to be shielded from intense solar radiation and stay clear of supernovas, which can emit the equivalent of 10 billion years of sunlight in a single blast. Interstellar dust would also have to be endured by the spaceship, causing its exterior to weaken over 2,000 years. One advantage of going at extremely high speeds is that time passes considerably more slowly for the person moving than it does for those who are left behind. At 70% the speed of light, only 1,428 years would go by on the spaceship, compared to 2,000 years on Earth. If a spaceship traveled at the much faster speed of 99.99% the speed of light, it would arrive at Kepler 452b in slightly over 1,400 years, as experienced on Earth. But its passengers would barely have aged a month. That would make space travel pretty convenient, if it were possible. What about the interstellar approach, though? Is it not possible for us to jump through a wormhole and hope for the best? Yes, but it's quite unlikely that will come to pass. If wormholes exist, they most likely developed as a result of a celestial explosion or star collapse. In the end, although reaching Kepler 452b would be an incredible feat, humanity would be better served by colonizing a nearby planet. Jupiter is the biggest planet in our solar system. It's a bit of a brute. The weight of the gas giant is more than double that of all the planets in the solar system put together. Its enormous size and strong gravitational attraction allow it to retain 80 verified moons in orbit. To put that into further perspective, the radius of the fifth planet from the Sun, which is 69,911 kilometers, is roughly 11 times wider than that of the Earth, which is 6,371 kilometers. Jupiter would be roughly the size of a football if Earth were the size of a coin. Jupiter's surface area is 61.42 billion square kilometers, while Earth's has 510.1 million square kilometers. But the Sun is still considerably bigger. While Jupiter's diameter is around 11 times larger than the Earth's, it is around 10 times smaller than the Sun's. Yet while Jupiter is for sure the largest known planet in the solar system, there are bigger ones out there. But how much bigger? What is the biggest known planet? Meet ROXs 42BB, a gas giant 460 light-years from Earth that orbits M-type star. Its radius is roughly 3 times that of Jupiter, while its mass is approximately 9 times that of Jupiter. This gas giant is located near or orbiting the very young star ROX 42b, which is about 1.34 times as wide as our Sun, but cooler and dimmer. The star is a member of the Ophiuchus star-forming region located in the constellation Ophiuchus. It is, however, 30 times further from the star than Jupiter is from the Sun. Its orbital distance from the star is 140 to 157 astronomical units. For comparison, Pluto orbits at a distance of about 30 to 49 astronomical units. Given its distance, it probably comes as no surprise that it takes 1963 years to complete one orbit of its star. This situation is a little bit different than deciding if Pluto is a planet. For Pluto, it is whether an object of such low mass amongst a group of similar objects is a planet. Here the question is whether a large object that is that far from its home star is still a planet. If so, then how did it form? The amazing thing about this planet is that it was observed directly in 2013 by Thane Curie, an astronomer from the University of Toronto, and this object might be a background star or a second planet. It is currently unclear if this exoplanet is a planet or a failed star, despite the fact that it appears to be below the mass limit of a brown dwarf. The reason why brown dwarfs are sometimes referred to as failed stars is that they're formed like stars, but don't have enough mass to ignite nuclear fusion reactions in their core. A star is formed when gas and dust are drawn together by gravity to form a dense core that finally heats up enough to start nuclear fusion processes. The star shines brilliantly as a result of this process, which releases an immense amount of energy. Brown dwarfs are objects that form in the same way as stars, but they lack the mass needed to sustain nuclear fusion reactions in their cores. Without these reactions, they're unable to shine like stars, and they eventually cool down and become dim objects in space. It remains unknown to astronomers whether ROX 42Bb originated more like a binary star or like planets through core accretion. The core accretion is known as the standard model of planet formation. The model starts with a disk of gas and dust called a protoplanetary disk that surrounds a young star. Because the initial formation of the core takes a long period, core accretion is most effective in nearby regions of the parent star. Due to gravitational forces, the gas and dust in the disk gradually clump together to form larger and larger objects. Through mutual collisions, these objects, often referred to as planetesimal, keep growing until they are at least 1 kilometer in size. Once a planetesimal reaches this size, its gravity becomes strong enough to attract and hold on to gas from the protoplanetary disk, rapidly increasing its mass and size. This process is called gas accretion, and it eventually leads to the formation of a gas giant planet like Jupiter. Disk instability, the process by which a fragment of disk gas encircling a young star directly collapses under its own gravity into a planet, is an alternative theory put out for the formation of gas giant planets. The farther from the parent star this mechanism operates, the better. Nonetheless, it is believed that smaller rocky planets, such as Earth, evolved by a distinct version of the core accretion process. In this situation, the planetesimo keeps growing as a result of collisions until it reaches a size where its gravity is powerful enough to attract gas. Therefore, it transforms into a rocky planet with a tiny atmosphere rather than a gas giant. However, ROX 42Bb might as well be a brown dwarf if it formed like a binary star. A binary star formation occurs when two protostellar clouds collapse together, forming two separate clumps of gas and dust. As the two clumps continue to collapse, they begin to orbit each other and become gravitationally bound. Over time, they continue to accrete gas and dust from their surroundings, increasing in mass and size. One of the clumps has the potential to become a star if its mass surpasses that of the other, whereas the less massive clump will turn into a brown dwarf. This occurs because, in comparison to the less massive clump, the more massive clump is able to reach the temperature and pressure required for nuclear fusion to occur in its core. Otherwise, both clumps may turn into brown dwarfs. If both of them have roughly the same mass and neither is massive enough to start nuclear fusion reactions in its core. In this case, the two brown dwarfs will stay in orbit around one another and create a binary system. The large size and mass of this gas giant make it a very mysterious candidate. Nevertheless, the exoplanet is not too big to be a normal brown dwarf, which makes it difficult for astronomers to understand how this object evolved as Jupiter did. Accordingly, the exoplanet might be a member of a previously undiscovered planet class, or it might simply be an extremely rare, low-mass brown dwarf that develops similarly to other stars and brown dwarfs. While scientists continue to look for habitable, Earth-like planets surrounding other stars, they may have just identified the most inhospitable planet to date. It is a world like no other. The planet, which is twice as big as Jupiter and has a temperature higher than that of most stars, is sweeping across space, while a massive tail of extremely hot gas stretches behind it. Life as we know it would not stand a chance. Known as Kelt 9b, this planet was found in 2017 and is located in the constellation Cygnus, some 670 light-years away. Kelt 9b is a gas giant world about 1.8 times bigger than Jupiter, with 2.9 times its mass. It orbits a hot B-type star named Kelt 9. Its star-facing side reaches temperatures almost as hot as our own Sun. Prior to the discovery of Kelt 9b, there are only 6 known planets that revolve around a type stars, which can have temperatures as high as 10,000 Kelvin on their surface. Known to be the hottest star to support a transiting exoplanet, Kelt 9 has roughly twice the mass, size, and temperature of our Sun. Given its high temperature, Kelt 9 would appear vivid blue to an observer on Earth if they could view it with the naked eye. Such hot stars are not good candidates for planet hunting because their spectra tend to rotate quickly, making it more difficult to detect the back-and-forth drag of circling worlds, and because there are few landmarks in them. But a team using the Keeler Degree Extremely Little Telescope, KELT, an array with instruments in Arizona and South Africa, got lucky when it spied Kelt 9, with a surface temperature of 10,200 Kelvin. Its rotational speed is 38 times faster than that of the Sun, taking only 16 hours to complete one full rotation, compared to the Sun's approximately 30-day duration. The star's shape is distorted by its fast rotation, which causes it to widen in the middle and flatten at the poles. This results in a process known as gravity darkening, when the star's equatorial region cools and becomes dimmer, while its poles heat up and become brighter. As a result, there is an almost 1,500 degrees Fahrenheit temperature difference across the star's surface. Scientists are particularly interested in this phenomenon known as gravity darkening or brightening. Kelt 9b experiences the whole range of star temperatures twice every orbit, resulting in an almost unusual seasonal sequence. When the planet swings over each heated pole, it experiences summer, and when it travels over the colder middle part of the star, it experiences winter. Thus, Kelt 9b has 2 summers and 2 winters per year, lasting roughly 9 hours each. Kelt 9b begins its transit near the star's bright poles and then blocks less and less light as it travels over the star's dimmer equator. The researchers was able to reconstruct the star's out-of-round shape, orientation in space, range of surface temperatures, and other factors affecting the planet thanks to this asymmetry, which also offers clues to temperature and brightness fluctuations throughout the star's surface. Scientists saw the shadow of a planet, Kelt 9b, pass in front of it every 1.5 days. The researchers calculated that Kelt 9b is around the size of Jupiter, based on the shape of the brightness dip. However, in order to find its temperature, they used an additional measurement. The planet's brightness, which they calculated by measuring how much the brightness of the system dropped when Kelt 9b passed behind its star. This figure, 0.1%, helped them in estimating the planet's daytime temperature, which is approximately 7,800 degrees Fahrenheit or 4,300 degrees Celsius. That's hotter than the surfaces of some stars, and the hottest giant planet ever discovered. It's so hot that its atmosphere certainly boils away into space. Molecules like water, carbon dioxide, and methane cannot develop there due to the intense heat. Rather, metal atoms float through the air. The intense UV radiation from the burning star is most likely also destroying the atmosphere. In fact, this heat may cause the planet to lose mass at a rate of anywhere from 10 billion to 10 trillion grams every second. The majority of the planet may vanish after 300 million years, possibly leaving behind a rocky core. Though Kelt 9b will teach scientists a lot about planetary systems very different from our own, don't expect it to deliver any insights on alien life. Astronomers have been searching for a planet similar to Earth for a long time. Every time there's an unexpected surprise. Few have supergravity, and some of them have 2 stars. The issue with exoplanets is that they are much fainter and smaller than their star. Scientists use an excellent technique known as the transing method in that situation. Using that procedure, you see a distant star and record its brightness. The planet, if any, that revolves passes in front of the star and blocks part of its light, causing the star's brilliance to decrease. It might be negligible, but it must. In the same way, astronomers examined data of a gas giant orbiting a far-off star in 2011. Upon examining the star's brightness, scientists discovered a strange phenomenon. It seemed to be that the rotating planet was consuming the star's brightness. It reflects less than 1% of light falling on it. Welcome to TRES 2b, the planet of eternal darkness, which lies in the Draco constellation around 750 light-years away from Earth. This hot Jupiter exoplanet is almost as dark as the darkest artificial material on Earth and significantly darker than coal, reflecting less than 1% of the sunlight that strikes it. This specific material absorbs 99% of all light that hits it in the optical, ultraviolet, and infrared spectrums. TRES 2b absorbs all but 0.1% of the visible light that comes its way, while coal, one of the darkest materials on Earth, reflects just 5% of the visible light that strikes it and absorbs 95%. Nevertheless, despite its darkness, TRES 2b glows thermally because it orbits so close to its star. The reason it differs from other similar-sized planets is that Jupiter, for example, is surrounded by ammonia clouds that reflect more than 1/3 of its sunlight. TRES 2b has no ammonia clouds to reflect light because it is extremely hot. Because it orbits its star at a relatively close distance of 5 million kilometers, it experiences temperatures as high as 1,000 degrees Celsius. But TRES 2b is not completely black. Because of its intense heat, it emits a faint red glow that looks like burning embers. TRES 2b's dimness suggests that the planet is strongly influenced by a still mysterious atmospheric component characteristic of hot Jupiter planets that absorbs an extraordinary amount of visible light, but had not been previously identified in TRES 2b. If the data from the recent study are accurate, what exactly is causing the atmosphere of the new planet to be so dark? The planet's atmosphere may contain gases like titanium oxide or vaporized sodium and potassium, which are light-absorbing chemicals that may contribute to the planet's extreme darkness. Still, the intense darkness cannot be explained by the existence of these chemicals alone. As is customary, sunlight is being absorbed by something on the planet rather than reflected. What that substance is still a point of contention. But whatever it may be, it isn't of Earth. Outside your spacecraft's windshield, the sky is mostly dark. The planet you are looking for is 4.65 billion kilometers from its sun. Almost no light reaches it. All of a sudden, you see a glow in the distance. It gets bigger and stranger as you get closer. You can see a shining pink light in front of you. As you go closer, you see what's emitting this glow. It's a magenta-colored planet. Welcome to GJ 504b, a giant planet located approximately 57 light-years from Earth. It is of a deep magenta color and is nearly 4 times more massive than Jupiter, with an effective temperature of roughly 460 degrees Fahrenheit or 237 degrees Celsius. It orbits around GJ 504, a G0 type star in the constellation Virgo that is slightly hotter than the Sun and barely visible to the human eye. The star lies 57 light-years away, and researchers estimate the system is about 160 million years old, based on methods that link the star's color and rotation period to its age. After HD 189733b, this planet is the second one whose color has been directly observed by scientists. This discovery would be notable only for that. What's perhaps more remarkable is that the planet itself casts doubt on accepted notions of planetary creation. Rather from being observed by eclipsing its parent star, it is actually the smallest planet that has ever been directly observed with a telescope. Astronomers have found other planets outside of our solar system that looks like Jupiter. These planets seem to be very common throughout our galaxy. This planet is unique though because it is roughly 43.5 times further from its star than the Earth is from the Sun, or 4.05 billion miles away. If it were in our own solar system, it would be beyond the orbit of Neptune. That's what poses a problem for astronomers. Core accretion theory is the current concept for the formation of planets the size of Jupiter. As we have already discussed, the problem is that Neptune's orbit lies just beyond the range of distances at which such planets may develop from stars. When they're out further, the debris is estimated to be too dispersed to form a planet as massive as Jupiter, because there's just not enough stuff out there to accumulate. And yet, there's GJ 504b sitting at a distance much further away from its star than Neptune does ours. This is one of the planets that is most challenging to explain under the standard framework of planet formation. Its discovery suggests that we should re-evaluate some of the basic principles of the core accretion theory, or thoroughly investigate alternate formation theories. Thanks to these observations, astronomers are learning a lot more about planets outside of our solar system. They might also have to reconsider how those planets evolved as a result of the process. Our universe is full of lots of weird solar systems totally unlike our own. With each new discovery of exoplanets, it's getting weirder. Next on the list is HR 5183b. This exoplanet is roughly 7.7 billion years old and at least 3 times as big as Jupiter. It travels a long looping path around a star in the Virgo constellation that is located roughly 100 light-years away. The exoplanet's orbit is incredibly eccentric compared to that of our solar system, where Earth and the other planets move around the Sun in nearly circular paths. If this massive planet's orbit were located inside our solar system, it would approach the Sun closer than Jupiter and then swing outward beyond Neptune's orbit. Its wild orbit gave it the nickname of the Whiplash Planet. The star's gravitational pull causes its movement around HR 5183, its host star, to whiplash, meaning that when it approaches the star, it accelerates, slows down, and then repeats the cycle. The astronomers have been watching the planet's star, called HR 5183, since the 1990s, but do not have data corresponding to one full orbit of the planet, because it circles its star roughly every 45 to 100 years to complete one full orbit. Though other exoplanets with extremely elliptical or eccentric orbits have been observed by astronomers, but HR 5183b is the only one known to orbit its host star at such great distances. Planets are formed from disks of material that remain after stars develop. Thus, planets should have circular, flat orbits at first. For the newly detected planet to be on such an eccentric orbit, it must have gotten a gravitational kick from some other object. The most plausible scenario is that the planet once had a neighbor of similar size. As the two planets approached close enough, one of them expelled the other from the solar system, sending HR 5183b onto a highly elliptical orbit. Such an intriguing exoplanet's discovery shows how our knowledge of planets outside of our solar system is still evolving. Scientists are continually discovering worlds that are distinct from anything found in our solar system or other known solar systems. We learn from Copernicus that the Earth is not the center of the solar system, and when we continue to explore and find exoplanets in other solar systems, we expected that these systems would be carbon copies of our own. But it's just been one surprise after another in this field. This recently discovered planet is just another illustration of a system that differs greatly from our solar system, but nonetheless possesses unique characteristics that contribute to the extraordinary diversity of our cosmos. The HR 5183b system is evidence of the incredible variety of planetary characteristics found in our galaxy. Not only this exoplanet an important finding, but it also serves as an important reminder that our knowledge of planet formation and evolution is still quite limited. There are planets out there that make us reconsider our assumptions and give us new perspective on the universe. It's a thrilling time for exoplanetary science, and as we continue to monitor HR 5183b, we anticipate uncovering even more about the mechanisms that shape planetary systems. About 4.5 billion years ago, our solar system formed. 4.5 billion years seems like a long time to us. It is nearly impossible for our minds to grasp just how long 4.5 billion years truly is. Even if you were to live to, say, 100 years old, that would only represent 0.022% of the total lifetime of the solar system. Even though our solar system appears to be quite old, it is not even close to being as old as the universe's oldest planet. A planet so old that it outlived its own sun. A planet that was born before many elements like carbon and silicon even appeared in sizable quantities. It was born almost immediately after the birth of the universe. This amazing planet exists literally right next to us. The universe didn't even have oxygen yet, but that planet already existed. The exoplanet known as PSR B1620-26b is the oldest planet ever discovered in the universe. It is 2.8 times older than our solar system, with an estimated age of 12.7 billion years. It has also been nicknamed Methuselah, after the oldest character from the Bible. Unlike most exoplanets discovered, Methuselah does not orbit a typical star. It orbits two different objects, making it a circumbinary planet instead. However, these two objects are not main sequence stars. Instead of stars, Methuselah orbits two stellar remnants, a white dwarf and a pulsar. Pulsars form in the aftermath of a supernova, while white dwarfs form from stars similar to the Sun. It's interesting to note that Methuselah was among the first planets discovered outside of our solar system. Methuselah was discovered in 1993, and similar to other planets discovered at that time outside of our solar system, its existence was confirmed by the use of the radial velocity method. The radial velocity method uses the Doppler effect to look for evidence of exoplanets. While we generally think of planets orbiting stars, planets also exert a gravitational pull on their stars. The radial velocity method looks for any wobble in a star's movement caused by the gravity of an orbiting planet. Though a star's movement caused by a nearby planet is minuscule, it can be detected by sensitive technology by observing the star's light. The Doppler effect explains how an object's light will change in wavelength based on its motion's direction and speed. An object's light will be blue-shifted and compressed as it approaches you. The same object's light will be red-shifted and stretched if it moves away from you. Therefore, when a planet exerts force on its parent star, the star's speed will change in relation to us, enabling astronomers to determine the Doppler shift of the star. In the case of Methuselah, astronomers observed a Doppler shift in the light of the nearby pulsar, and calculations showed that the most likely explanation was that a planet was exerting a gravitational force on the pulsar, causing it to move ever so slightly. Methuselah is special not just because it is the oldest planet ever discovered, but also because it is the first planet ever discovered to orbit multiple objects and within a globular cluster of stars. The Messier 4 globular cluster, which is 5,600 light-years away in the summer constellation Scorpius, is thought to be 12.7 billion years old. Because globular clusters formed so early in the universe, heavier elements have not been fully cooked in the nuclear furnaces of stars, which is why globular clusters lack heavier elements. Because of this, some astronomers argue that planets cannot exist in globular clusters. This conclusion was bolstered in 1999 when Hubble failed to find close-orbiting, hot Jupiter-type planets around the stars of the globular cluster 47 Tucanae. It now appears that globular clusters may be home to many gas giant worlds, circling farther from their stars than previously thought. Astronomers may have simply been searching in the wrong area. In addition, globular clusters can contain thousands to millions of individual stars, with the structure remaining intact for billions of years due to their mutual gravitational pull. Most stars within globular clusters likely formed within the cluster itself, and so any planets that orbit within the globular cluster are likely the same age. Accordingly, Methuselah is thought to be 2.8 times older than Earth, and the oldest planet ever discovered. Because it was formed so early in the life of the universe, it probably doesn't have abundant quantities of elements such as carbon and oxygen. It is highly unlikely that the planet might support life because of these factors. Even if life arose on, for example, a solid moon orbiting the planet, it is unlikely to have survived the intense X-ray blast that would have accompanied the spin up of the pulsar. Unfortunately, the magnificent history of this planet, which began almost at the beginning of time itself, is unlikely to have been witnessed or recorded by any civilization. A few times more massive than Jupiter, this planet has withstood the harsh environment of a globular cluster, a gravitational collision with a binary system, and the demise of its parent star. The planet was similar to Jupiter in a few aspects. It is probably a gas giant without a solid surface like Earth, and its mass is 2.7 times that of Jupiter. It takes around 100 years for it to complete one orbit, with a distance of 2.1 billion miles or 3.4 billion kilometers. Not much is known about this ancient planet other than its age, mass, and distance. After falling into the dense core of the cluster, where stars are so close to one another that they are only a few light years away, the star and planet orbited untouched for about 10 billion years. This star system wouldn't have been independent for very long before bumping into something, much like walking into a busy marketplace. As it passed by a binary system containing an old neutron star and a white dwarf, gravitational forces pulled the two systems together into a web of tangled orbits. Soon, the more massive progenitor star knocked the small-mass white dwarf out of its original position and ejected it into space. In the meantime, the planet was propelled into a circumbinary orbit, which circles both the neutron star and its original star. The new system of the planet, its sun, and the neutron star recoiled from the ejected white dwarf, in much the same way a cannon jumps backwards when it fires a cannonball. Reducing the likelihood of another such stellar interaction, this gravitational recoil sent the new binary system out of the core of the globular cluster and into a less dense area of the cluster. The planet gradually traced out a wide orbit around the neutron star and its parent star at a distance of around 2 billion miles from its new location in the cluster, which is comparable to Uranus's orbit around our Sun. Throughout the course of the following billion years, the planet saw the death of its parent star from this perspective. Matter rained down on the neutron star from the Sun-like star as it grew older and turned into a red giant. As the neutron star gained mass, it began to rotate on its axis more quickly and eventually spinning up into a pulsar. The neutron star is now rotating on its axis at a rate of about 100 revolutions per second, which is 10 times quicker than a hummingbird flapping its wings. Once all the excess gas left the star, it became a small, bright helium-core white dwarf. All the while, the planet continued on its sweeping orbit. This is the condition where the planet was found by astronomers less than 1 billion years ago. So how could researchers tell that this planet had survived such dynamic cosmic forces or existed at all? Using Hubble data, scientists used the white dwarf's color and temperature to determine its age and mass, which they compared to the wobble of the neutron star. In addition, radio studies of the pulsar revealed irregularities in its signal that could not be caused solely by its white dwarf companion's star. By combining all of this data, scientists were able to determine the tilt of the white dwarf's orbit, and consequently, the tilt of the third orbiting body. From there, astronomers were able to determine the mass of the third body, which is too small to be a brown dwarf or a low-mass star. Thus, the planet revealed itself through its subtle tug on the system. We probably would never have found this planet if it had just stayed with its original star. Its past positioned it correctly, and our interactions made it easier for us to see. In addition, we can learn about the planet's past from its orbit and location inside the globular cluster. The white dwarf must have lost its gaseous envelope after it, and the planet joined the neutron star in order for the suggested scenario to make sense. Evidence suggests that this is the case. As a result, the white dwarf should be young, bright, and low mass. Additionally, the planet's wide orbit makes it more susceptible to the gravitational pull of neighboring stars. If this is the case, the planet's continued existence indicates that the system has been in the lower density region of the cluster ever since its current configuration was formed. We can determine the time scale for the current configuration, the turbulent chain of events leading up to the present, and an age for the planet, because such a system would return to the cluster's core on a time scale of 1 billion years. And we know that the system has not yet returned. The history of this planet also helps astronomers determine the potential locations and numbers of planets. The planet was formed before to the existence of many heavier elements in space. Its birth in an element-poor globular cluster like M4 could indicate that planets are more prevalent in these kinds of environments than previously believed. This is a clear indication that there are more out there. There are 100 pulsars similar to the one this planet orbits. This one was simply very well researched. The universe is home to over 100 billion galaxies. On average, galaxies contain anywhere from 100 billion to 1 trillion stars, and astronomers believe that most stars are orbited by one or more planets. This makes it very unlikely that Methuselah is a unique world, and there are likely countless other worlds that predate the formation of our solar system by billions of years. It's amazing to wonder what these worlds may have experienced over the course of their existence, especially when we consider the sheer amount of change that the planets in our solar system have experienced in their 4.5 billion year history. With the advancement in space technology, the count of confirmed planets is in the thousands and rising. That's from only a small sampling of the galaxy as a whole. The universe contains countless worlds experiencing countless moments. And we are living in a universe of exoplanets.